starting. All right, so definition of a Hilbert plane. Have a geometry where your incidence axioms, betweenus axioms, and congruence axioms all hold, and then you get for free all of the resulting propositions that we've talked about previously. Now, here are some of the things that you want to worry about or be aware of in a Hilbert plane. First thing is, notice the axioms that are included and the axioms that are not included. So the majority of the Hilbert axioms that we've talked about are definitely included, incidence, betweenness, and then those 6 congruence axioms. But our parallel axiom or Playfair's axiom is not included here. So the buzzword that we've seen in the past, this would be us looking at something called neutral geometry. You don't need to worry about that buzzword. If you wanted to tie this into stuff we've talked about in the past, that's the term. The other thing to watch out about is circles. So as of right now, we totally have had a definition of circles, and in fact, a while back we actually looked at what would a circle look like in some of our various models, and in some of them we decided that, hey, it looked really, really stupid, like squares and diamond shapes and weird dotted lines, etc. What we don't have yet, and I see your question and I'll get to it in just a second, what we don't have yet is whether those circles are going to be guaranteed to intersect with each other. So for example, suppose you have 2 circles, and I really should have drawn the first one as sort of a bunch of dotted points. And maybe the second one is, again, pretend that kind of looks like a circle. But if maybe it's not something that's continuous like you think of in the standard model of R2, in other words, when you're on the XY plane before R class, maybe it's only points that are, oh, I don't know, how about in Z2? So the only points on this circle line are if you have integer values for the 2 coordinates. Or maybe like what you guys had in your homework, maybe you're in Q2, so you only have your X and Y coordinates come from fractions. So you don't actually have everything that you would normally think of on that circle. In those cases where you have these gaps, what can happen is the circles can be positioned in such a way there's no point that's shared between the 2 circles, so they sort of like miss each other. It's like some of the 3D puzzles that are tricks where you're having things that are intertwined and you try to take them apart, or like magicians who do things with what look like circular rings but actually have holes in them so they can put them inside of each other. Or interlocked with each other. It's that sort of issue. So while we know what a circle is and we can define a circle in whatever model we have for our Hilbert plane, what we don't have yet is any sort of guarantee that the circles will actually have an intersection. Now, before I comment on that anymore, let me do a quick hiatus. We'll talk about Playfair's axiom to remind yourselves what it is, and also I'll give you a quick foreshadowing of our axiom that deals with circles. So one of the handouts in this section is, and it's posted up on Canvas for you guys too, it's just all of the Hilbert axioms typed up. If you've already done this, awesome, no worries. I've typed this up in the past just to make sure I can hand it out in class and everybody literally has the axioms in front of them during class. But if you already have it somewhere else, you're already set. So you've got your 3 incidence axioms dealing with points. You've got our 4 betweenness axioms that deal with how 3 points interact with each other on a line. We have our congruence axioms, the 3 with line segments, the 3 with angles. And then here are all the extra guys. We've had 2 of these so far. The first one is Playfair's axiom, or as your author now calls it for the rest of the book, parallel axiom. This is the one that says you've got some line L, you've got some point A. You're going to be able to find either no line that is parallel to L that also contains A, or you'll find one line. Okay? And then remember when we were dealing with affine planes, we actually did the stronger version of Playfair's axiom. This one says you'll always get exactly one line parallel to your given line through your given point. So those are the 2 axioms we've had already. The axiom that's going to give us what we want with circles. In other words, if you have 2 circles, they're going to actually intersect each other if the conditions are right, is this guy called, in terms of symbols, axiom E. I'm not sure why it's called axiom E. There's nothing E about the name of it. It's also called the circle-circle intersection property, and it's going to give us the conditions that you need in order to guarantee your circles to intersect with each other. Notice this is not one of the axioms that is required, that you're required to have to be a Hilbert plane. So there's definitely Hilbert planes where circles don't play nicely with each other. There's also Hilbert planes, notice, that don't necessarily have Playfair's axiom holding, so parallel lines don't play nice with each other. So if you need either of these two things to occur, circles playing nicely or parallel lines playing nicely, you actually say things like, I have a Hilbert plane plus axiom E, or I have a Hilbert plane plus axiom P. Okay? So you'd add in the extra condition that you need. Now, the last two Hilbert axioms that we have are actually called Archimedes' axiom and Dedekind's axiom. We are not going to deal with the Dedekind's axiom, although feel free to read about it in your book. Your author talks about it a little bit. And we're not going to deal with Dedekind's axiom because if Dedekind's axiom holds in your model, it turns into you basically just have a copy of the standard model on R2. And that's boring. Okay, so we're not going to force ourselves to use Dedekind's axiom. Archimedes' axiom we're not going to use very much, but in terms of when it would be used, I'm going to let you guys read through it a little bit here or on your own, but this guy would be when you're dealing with things like similar triangles where you're scaling up or scaling down things. So notice what that means. Right now, we're not going to be using similar triangles. We will get to them in the future, and we'll talk about what all that means. But in terms of everything together, I went ahead and put all of your Hilbert axioms together on this document. All right, so there's our aside. Going back. So the regular Hilbert plane, notice it doesn't have any of those extra axioms on that second page. So if you want Playfair's axiom, or as your author now calls it, parallel axiom, you have to include it. If you want circles to be playing nicely together, you'll have to include that axiom E, which we'll talk about that axiom E that deals with circles on Monday. And this is what we actually already said. We have circles, but we have no guarantee that they intersect with each other nicely, or at all. And that actually includes circles and lines intersecting as well. All right, so relationship of Hilbert planes and then the stuff back in Euclid's Elements. Now, remember what we're actually trying to get to. This Hilbert geometry stuff was Hilbert going back to geometry and saying, you know what, Euclid, he did awesome stuff, but it's specific to just when we have a piece of paper, a pencil, a straight edge, and a compass. What happens if we have other situations, like three-dimensional geometry, or if we're on a sphere, the surface area of a sphere, as opposed to on a flat table, per se? What do we need? What can we do here? Now, in terms of what Hilbert did, we are actually progressively building back to recover the model, notice the word model there, of the geometry that Euclid put together. So that geometry that we were dealing with in classical geometry, that geometry that Euclid put together, that's actually one specific model inside of Hilbert geometry. Okay? What that means is eventually we're going to have to get back all those results. So here's the first tie-in. It says if you have some arbitrary, so any old Hilbert plane you want, so as long as the incidence, betweenness, and congruence axioms all hold, then we can actually prove or we can show that all of the propositions up to 28 from Euclid's Book 1 also work in the model. Now that's a little bit of a lie because I said all of the propositions up to 28, and if you'll notice in that range, we're actually missing 2 of them. So comments about those 2. The first proposition that we're missing is proposition 1, which is the construction of an equilateral triangle. Now to remind ourselves, to construct an equilateral triangle, we were back in classical geometry when we went over this guy, like first or second day of class, I don't remember which. We had what? We had the given base, we drew a circle, center one end, radius, this line segment. We drew a second circle, again, center is the other end point, and radius the same as before. And pretend those circles actually look like nice circles. Then what do we do? The third point or the third vertex of your triangle was one of the 2 intersection points of the 2 triangles. Now, any guesses why this is something we can't guarantee right now? Any guesses why we can't guarantee that very first proposition doesn't necessarily hold in a Hilbert plane? Hint, it deals with how we constructed the equilateral triangle. What did we have to assume in order to get that third point? Yeah, so the assumption here is we had to assume that the circles actually intersected. And what was that big expose that I probably rambled on too long about just a second ago? Right now in any old Hilbert plane, unless we have extra information, we can't assume that any two circles actually intersect. Now, if you have a specific case, maybe this would work, but you can't guarantee that it works for any line segment in your Hilbert plane yet. Okay? So that's why we actually don't have this first proposition. Or we can't guarantee that that first proposition will actually always hold for creating any equilateral triangle in your arbitrary Hilbert plane. Notice the arbitrary Hilbert plane means we haven't gotten into your model yet. So it has to be, so this statement has to be true for all Hilbert planes. Excuse me there. All right, so the other missing proposition is proposition 22 from book 1, and this one is constructing a scalene triangle. Now this one we didn't actually talk about in class, but it was in that first homework set, the packet of the bazillion and one sort of tutorial of how to use your compass and straight edge. And what it says is it says you've got 3 line segments, and you can assemble those 3 line segments in such a way that you formed a triangle. Now, what was the procedure? You have to take one of the line segments as your base. You randomly pick another line segment. I'm going to pick the middle length one. And you make a circle centered at one endpoint, radius the same as that middle line segment. And then repeat the process for the smallest line segment, so center other endpoint and radius the same as that little line segment. And pretend I'm not freehanding it and that looks terrible. Then the resulting triangle is the intersection of the 2 circles, and you then draw on the resulting sides. So this guy is also a proposition we can't guarantee holds in your arbitrary Hilbert plane. Why? Because if it held, it would say you would always be able to do that for any 3 line segments, or any 3 line segments under the condition given in that proposition. So anybody have a guess on why this one fails to hold in any old Hilbert plane? Yep, it's the exact same reason as the last one. It's the whole reason this construction works is you are assuming that the circles will intersect. Arbitrary Hilbert plane, there's no guarantee that those circles are going to intersect. Maybe they actually do in specific examples that you try and you test, but they're not guaranteed to work in any old Hilbert plane with any old line segments. So same reason. But we have all of the other propositions other than 1 and 22 but, for the first 28 propositions in Euclid's Book 1. So this does include a lot of stuff. It includes things like side, side, side. Technically it includes side, angle, side, but we already had that with one of our Hilbert axioms. It includes some stuff up here with parallel lines, and it includes a number of stuff with triangles. Okay. So the main thing we're going to talk about today, or really the rest of today, is dealing with Hilbert constructions. So Hilbert constructions are both similar and different to the constructions we've done in the past. So let's compare and contrast, and also give you the information you need. So first thing is to remind ourselves where we've been. The classic constructions back when we were dealing with Euclid's elements or Euclidean constructions always dealt with a compass and a straight edge. Those were your 2 main tools. Of course, you had your piece of paper and something to write with, so your pen or your pencil, but your specific tools that you used were the compass and the straight edge. Now, here's the deal. I'm not going to assume that you guys actually have any tools other than a compass and straight edge, so I'm going to show you how to use these 2 tools to mimic the actual Hilbert tools, because the actual Hilbert tools are a little different. So first Hilbert tool is an axiom. Actually, all 3 of the Hilbert construction tools are axioms. So first axiom is incidence axiom number 1. To remind ourselves, incidence axiom number 1 says you have any 2 points in your geometry, you will be able to find the unique line that contains those 2 points. In terms of a physical tool that you would use to draw with, this is exactly the same as using a straight edge. So at that point, no difference than what you would do back in our classical constructions. Here's where everything changes. The second Hilbert Construction tool is axiom C1 or congruence axiom 1. That guy is copying a line segment. So you're given some line segment, you find some ray somewhere else in your geometry, and you copy your line segment over on that ray. Okay. Now, can we do that with a compass? Of course we can. Here's, though, the actual tool. The actual tool that we would use to do that copying of a line segment is something called a pair of dividers. A pair of dividers looks almost exactly like a compass. Pretend that doesn't look as terrible as it does. Okay? So pretend you have a compass, but here's the difference between the pair of dividers and an actual compass. You know how on like the feet of your compass, one of them should be a pointy spike that potentially could hurt you very badly if you accidentally stab yourself with it? And the other one is typically a pencil or pen or whatever writing instrument you have on the other end. A pair of dividers is a compass, except your writing instrument, so pretend that's where your pencil lead was, is not a writing instrument, it's a second pointy end. So this is exactly the same thing as a nautical compass. So if you've ever seen movies or been physically on boats and you've got somebody with a map, and they've got something that looks like a compass that they're walking across the top of a map, they're not actually normally drawing on that map. The compass that they're using actually has 2 spiky ends, and they're using it to measure off distances. That's the pair of dividers. Notice the advantages and the disadvantages of this pair of dividers. The advantages is that it can totally take your line segment from wherever, and it can measure off whatever that distance is and find where the new point needs to go on the ray. That's no worries. Okay? What it cannot do, though, is it cannot draw a circle because you don't have that writing instrument on the second edge. So how would you use a normal compass to mimic a pair of dividers? Because I'm not assuming you have a pair of dividers, although if you do, awesome. Just don't draw circles with your compass. So that's literally the thing here with C1. Don't draw circles with your compass. If you want to copy your line segment, just do the normal copy of the line segment. Yeah, so if we were in class, I would show you that I do not have a pair of dividers. I used to. I'm not sure where it went. Probably somewhere really inconvenient, and one day I'm going to stab myself terribly when I find it. But I would be showing you that I'm just going to use a compass for this one too. The warning, though, is don't use your compass to draw a circle. Now, the third and last Hilbert Construction tool corresponds to congruence axiom number 4. So congruence axiom number 4 was the first congruence axiom that dealt with angles. So for this guy, and I'm going to go ahead and throw in the name of the tool that it corresponds to, but let me go ahead and put the picture of what it would do. You're given some angle, you have some ray, you go ahead and you copy your angle over onto the ray so that it matches. Okay? Now, the physical tool that corresponds to this axiom C4 to copy angles I want to say yes, but I'm also, as soon as I want to say yes, pulling a full blank in terms of that phrase. So I'm going to draw the picture, and you double check that I'm actually thinking yes is correct. So a transporter of angles looks as follows, and it totally is something you can see in construction tools too. If you've ever done anything with construction, you may have seen this. What it looks like is 2 rulers that are joined together with a hinge. Okay? Okay, that looks terrible. Pretend you have 2 rulers that are joined together with a hinge. Yes, awesome. So I was thinking yes correctly. My dad does carpentry, and I was having this moment. All right, so yes, what it does is you've got these 2 things that look like rulers, and you've got the hinge at the end, and you can literally move those two parts that look like rulers out, wide, skinny, whatever, and then you can set and lock it. Some of these things actually have a locking mechanism right here. Some of them don't, and the hinge is just stiff. It's the same thing of when you guys have discovered good and bad compasses. Some of them are awesome when you move the legs back and forth, and some of them not so much. Right? So in terms of how you would use this thing, you would take your set angle right here. You would place one of the straight edges on one of the rays. You would then move the other straight edge right here so that it would be on top of the second ray. And then when you put it over onto the ray where you want to copy the angle to, put one of the two edges on the given ray, and then you take your pencil and you draw along just like you would with a straight edge on that second straight edge. Okay? I am not assuming you have one of these, but if you do, or if you're like a couple of my former students, like 2 of them over the last 5 years, so not many, and have actually made your own, that's totally fine. It'll actually speed up the work. It'll actually speed up your work in making your constructions. Okay? We're not going to do tons and tons of Hilbert construction. I lie. All of the rest of our stuff for constructions in the course are going to be Hilbert constructions, but if you don't have this tool, no worries. So if you don't have this tool, what would you do? Just use the shortcut method we did back in classical geometry to copy an angle to somewhere else. When I do it myself, because I don't have this tool either, I'll just use a normal a normal compass and do the shortcut copying of the angle like you would have to back in classical geometry. And that's the cheat. Okay. All right, so those are the 3 tools. Notice the big difference with the Euclidean constructions or the classical constructions and now the Hilbert constructions. It is we are very much using our axioms to create things. Now, do these correspond to physical tools? Yes, they do. Do the last 2, are they things that you can totally cheat and just use it with a compass? Yes, of course. Just don't use your compass to draw circles. So let's look at an example. And the first example that I've got for us prepped up is an isosceles triangle. Now, why do we talk about isosceles triangles? For several reasons. But let me go back to classical geometry for a second. With classical geometry and our classical constructions or Euclidean constructions, what did we say when we ran into issues? We said, when in doubt, if you have 2 points, draw a straight line. And if you have a straight line somewhere, draw a circle. Okay? So when in doubt, draw a circle was the previous directions. What have we just been saying about circles? Don't draw circles if your life depended on it. So opposite advice. In Hilbert constructions, instead of basing everything off of circles, our building block is going to be the isosceles triangle. So here, the rule of thumb is, when in doubt, draw an isosceles triangle. So let's look at how do we draw an isosceles triangle. So underlying assumption for all of the examples that I've got today, and none of them have this written in on the slides just because I forgot, we are going ahead and assuming that all of these guys are inside of some Hilbert plane. Doesn't matter which model, this is supposed to work in all of them. So if we want to construct an isosceles triangle, this particular construction starts off that we have the base of the isosceles triangle. Note, if you don't have the isosceles triangle and you just need to draw it totally from scratch, you would have to do a first step of, hey, let me get one line segment from my geometry. So we're going to assume that we're in a Hilbert plane, and let me go ahead and write that down, even though it's totally going to disappear as soon as I have the next fly-in. So in a Hilbert plane. I now wish I'd waited till I had to push the next button. Okay. So in terms of things that we have, let me write the in a Hilbert plane back here at the top. Hilbert plane. We are going to have our construction steps, just like what we had before. And over here, we're going to have our picture, except watch out. This is simply an illustrative diagram. Pretend I did not put a dot there. There's no dot over the U. Illustrative diagram. So remember how we've said the pictures and proofs don't have to be awesome constructions. They're just illustrative diagrams. That's now true of the picture with the construction. And specifically here, this picture is going to be in our model. That is our standard model. I guess I didn't need to actually write the word model there before the colon, on R2. In other words, it looks like the geometry that Euclid put together. So we want isosceles triangle. So we start thinking about what we need. Well, if you need an isosceles triangle, right now we have one side, the base, and 2 points. Well, to get to a triangle, you have to have a third vertex. So let's focus on finding a third vertex. So first thing I'm going to do is say, hey, let's grab an existence entity. And here I went ahead and chose the third incidence axiom. And I'm going to claim that the third incidence axiom guarantees us some point, call it D, some point that is not on the line that A and B are also on. Any guesses why I3 would be a nice incidence axiom to use? Anybody remember what that third incidence axiom said? So third incidence axiom just says you're guaranteed to have 3 points that are not all on the same line. So in order to have a triangle, you have to have 3 points that are not all on the same line in order to get it to be a triangle. Now, does this incidence axiom guarantee that point D will give you or get you to a isosceles triangle if you go ahead and find those lines AD and BD? What do you guys think? With that point D, how we found it in the geometry, are we guaranteed that now this triangle ABD is isosceles? Correct. There's no guarantee here that you're going to get an isosceles triangle, or at least not an isosceles triangle where AB is the base. It is possible, and in fact, in this particular orientation, it looks like that side AD is pretty close in length to side AB, but I mean, you could have a scaling triangle here, and that's totally fine too. Okay? So this is going to be our helper triangle. So if you remember way back when to one of our last constructions that we had previously to now, we constructed a golden triangle that had many, many steps. And we had a helper triangle that wasn't the golden triangle but got us there. Same deal here. This is our helper triangle. Okay? So we added in the extra 2 lines, the AD, the BD, went ahead and cited what construction step we used. And this here shows your reader, hey, these incidence axioms hold in any Hilbert plane, so I can do this in any Hilbert plane. It might not look exactly like my picture over here because the picture's in the standard model, but I can totally do this so far in any Hilbert plane. So next step is a comparison step. So according to Proposition 9.5, one of the last propositions we talked about last time that dealt with angles, it said many things, but one of the things this proposition said is pick any 2 angles and you'll always be able to figure out which one's the bigger angle, which one's the smaller angle, or if they're congruent. Well, if these 2 angles are congruent, there's no guarantee that they are, but if these 2 angles were actually congruent here at angle B and angle A, what would we have right now if those 2 angles were congruent? Anybody have a guess? Correct. If those 2 angles at A and B were actually congruent, we'd already have an isosceles triangle and we would be done. So we're not going to assume that. We're going to assume worst case scenario, and in fact, the most common scenario, which is one of the 2 angles is the bigger one. I don't know which angle actually is the bigger one. I went ahead and picked on angle B, saying angle B was the bigger angle, larger than angle A, simply because in this picture, that's what it looks like. But if that's not how you drew your picture, if your picture angle A was actually the bigger one, either flip the inequality or scratch off the A and the B and flip-flop them. But this proposition says you'll be able to figure out which is the bigger angle. Now, here's why we care about that step 4. That step 4 does nothing in terms of the construction. It just says, hey, I'm able to do this identification. So it's sort of a gray area of whether you include it or not. I went ahead and included it because we needed it for the next step. But sometimes I'll actually do this. Sometimes I'll actually put it in sort of brackets to indicate it's not really a construction step, but I still needed it. So step 5 here is we're going to copy the current angle A, and we're going to copy it over here to B. Specifically, you can either say the angle it's going to turn into, so notice point E is not up here yet, but that's going to be the copied angle. But you can also say copy it to the ray BA to tell your reader which ray you are copying it from. Make sure you copy the angle inside the current triangle, otherwise this doesn't work. So you go up, you'd figure out what the copied angle is, and you draw in the line. Now I'm actually going to have that fly in here in the next step, so here's how it goes. You draw, so here's the shortcut method if you're using a compass. You draw a circle centered at A. I just did the part of the circle that's inside the triangle. Draw a second circle centered at B, same radius. Again, I just drew the part of the circle that's inside the triangle. Then you put your compass at the intersection of that arc and one of the sides of the triangle at angle A. Measure off until you hit the intersection of the arc and the other ray. Then place the pointy end of your compass down here on one of the sides, actually the base here, AB, and mark off how far up you're going to go with that same radius that you had over here at angle A. If you do that, you will get then a point, which I'll go ahead and highlight there as point E. And if you go ahead and draw in the line that connects B and E, whether it's the full line or just a ray, that's the line that we're going to need to form our isosceles triangle. Specifically, we're going to grab the intersection of that line and the side AD that we already have. And I am going to claim that the resulting point C gives us our isosceles triangle. I'm going to claim here that triangle ABC is actually isosceles. Now, here's the things we know. We know that the angles A and the copied angle ABE, or if you prefer ABC, are congruent to each other. And if you have these two angles or any two angles of a triangle congruent to each other, anybody remember what that means? If you have a triangle and the only thing you know about it is two of its angles are congruent, what does that tell you about? This one tells you that your opposite sides of those congruent angles are also congruent sides. And if you have two congruent sides, that means you're definitely going to be an isosceles triangle. And that right there is totally from Euclid's Elements, proposition 6 from book 1. Now, remember what we said just a second ago. If we jump back to this thing about Hilbert planes, if you're in a Hilbert plane, we automatically have the propositions from book 1, propositions 2 through 21, and 23 through 28. Does that include our proposition 6 from book 1? Do we have that proposition 6 from book 1? Yeah, we do. So what that means is it is totally fine for us to use this proposition 6 right here and say, yep, we got these two congruent angles. That means we've automatically got an isosceles triangle right here. Now, there's one catch, and the one catch is you have to guarantee that that point C actually exists. Okay? So the next thing we're going to do is we're actually going to prove that this construction always works. And so that'll be the next slide. Any questions before we jump into the proof of why this construction works? All right, so just as a reminder, details here, you've got our picture. The picture is just an illustrative diagram in our standard model on R2. The actual main construction part are all of those steps. And don't forget the Hilbert axioms, because those guys right there are the things that make this work in any model that's a Hilbert plane. So this particular construction, yes, depending on what those angles are, you could potentially catch an equilateral triangle. If you are in the standard model on R2, the only time you would catch the equilateral triangle is in the one out of infinitely many possibilities of getting 60 degrees for both of the original two angles here at A and B. In other words, those two guys have to be congruent to each other. So it's really, really rare, but no, that should not mess up future things that we would use this for. That should actually still be okay. but that's literally one in a infinitely many possibilities. So while it definitely can occur, most of the time if you do this with an arbitrary point D right here, you're going to go ahead and just get a true isosceles triangle that's not also equilateral. All right, so let's look at the proof. So I went ahead and kept the copied picture over here to the side, went ahead and put in our T-chart, and just like when we did proofs of constructions back in classical geometry, went ahead and wrote down what we've already done. Notice, hey, we've got our given line segment. We pick our point that's not on that line segment. We've formed AD and BD. These are totally our construction steps. We assumed that the angle A was the smaller of the two angles, and then we went ahead and copied our angle A over here inside of angle B. This is exactly the same as our constructions that we've done so far. Now, here's the part of why everything works. So one of the things that I definitely forgot to put in here, but that should probably go right after that line, is that your angle A and your copied angle at B are actually congruent to each other. So once the rest of this stuff flies in, I'll go ahead and put this arrow over here and insert that guy right here by the line. But notice if you say copy, that's literally just the reasons are like construction steps. Or if you prefer, you could have rewritten this statement 6 to say copy angle. Actually, the normal way that you write statement 6 is this way. And I just did it shortcut to try to fit it on one line. I am now regretting that. So copy angle DAB to the ray, BA, and then you'd say something like such that angle DAB or angle A is congruent to the angle ABE. That's actually the most proper way to do it. And probably that's why I forgot to put in the sort of clarification step of, hey, angle A is the same as its copied version, or congruent to its copied version. All right, so next step. I am going to claim that point C exists. Any guesses why point C would exist here? This guy right here. Remember, we're in a Hilbert plane, so that means we have all the incidence axioms, we have all the betweenness axioms, we have all the congruence axioms, and then all of the results. Ooh, yes to crossbar theorem. So this one here is going to work because of crossbar theorem, and it's the order of how things went in. So here you drew the line first, and then you said, hey, I need to make sure that that line BE extended actually intersects your line AD. So watch out for order. Yes, you could totally pick a point C on the line AD, but there's no guarantee it's the point you actually need to make the angle the same as the angle at A. But yeah, crossbar theorem totally is something that would work right here. Now, second thing I'm going to claim at this point we could go ahead and just say that triangle ABC is isosceles. And we actually already talked about this. That is your proposition 6 from book 1 of Euclid. And note, we can use this guy right here, and some people like to include this step. I don't normally bother, but some people like to include the step that says, hey, we can use proposition 6 from Euclid's book 1 because of proposition 10.4. And proposition 10.4 was the one that said you can use that list of propositions from book 1 of Euclid. And that's it. That's the reason this works. Notice two things. Point C exists by crossbar theorem, and now the triangle is isosceles by essentially properties of isosceles triangles. Or really, it's the check for isosceles triangles. Okay. Questions? Make sense? Kind of feeling okay-ish. All right, well, let's look at another construction. I've got a little bit of theory before the next construction, but it's just more of a FYI. So things that we get for free. We're going to get for free side, side, side. Your book actually talks about the triangle property of side, side, side before he lists out all of the propositions from Euclid's book 1 that we get for free. So he actually goes through why side, side, side works in a Hilbert geometry, or excuse me, in a Hilbert plane. Okay. if you just like to reference Proposition 10.4 that we had earlier that just gave the list of all the propositions that hold from Euclid in a Hilbert plane, you get this one for free as well. Just like you also get angle, angle side, and angle side angle as well. You also get, and this is the one we just looked at, you get that an isosceles triangle will always exist on any given side or any given base, AB. Now, this proposition just tells you that you'll be able to find that point C to get the third point for the isosceles triangle. It doesn't tell you how. The example with the construction we just did, that tells you the how. How do I actually construct this isosceles triangle? So this is somebody that we're actually going to use quite a bit when we do Hilbert constructions in the future, and we'll see that in all of the rest of the examples that I've got lined up for us, where instead of drawing a bunch of circles, we're going to throw in isosceles triangles all over the place. And then the last piece of information from Section 10. Section 10, I believe, had only 4 propositions. We did the 4th one first, so we went backwards there. The 3rd proposition in Section 10 is the exterior angle theorem. And this one goes as follows. You have some triangle, grab any of its exterior angles, and that exterior angle is always greater than any of the 2 alternate interior angles. And note here in terms of that comparison, the greater than is that same inequality of angles that we talked about before, where the smaller angle can literally be copied inside of the bigger angle. And that's why we had to specify back here at step 5 of our previous example, which angle was smaller. That way we could copy it to inside of your triangle, and cross-bar theorem actually applied. Okay. And this one, I believe, is Proposition 16 from Euclid's Book 1, and side, side, side is Proposition 8 from Euclid's Book 1. Again, they both have names, which means you don't need to worry about the numbers if you don't want to. I would definitely not bother remembering the proposition number of the 10.1 or 10.3 because it's already got 2 other names. So that's the last bit of the behind-the-scenes theory. Everything else I've got in this section is more examples of construction. So, next construction, bisecting an angle. Notice I'm just going over the same basic constructions that we had back in classical geometry too. Okay. So here you're given some angle. I went ahead and called it A. Your angle has 2 rays. I just went ahead and put the B and the C down there. I didn't specify any points B and C, just so we could refer to which ray we're using. It doesn't matter, it just makes it so when you write out the steps, it's easier to read. So first thing that you would do is pick one of your rays. It doesn't matter which one. I picked the one that's tagged as B, and you pick some point on that ray. And I'm going to claim you can always pick some point on that ray because remember what the second incidence axiom said. It says any line has at least 2 points. So we've got 1 point on the line. This now gives you the second point on the line. Notice you will not be able to use this incidence axiom number 2 to get you another point on the line because now you've got your 2 points on the line. There's no guarantee there's more. Do we know there's more? Of course, but you'd have to use a betweenness axiom or one of the results like line separation. All right, so second thing we want to do is we want to go ahead and we want to copy that line segment AB, AD, to the other ray. So we'll pick some point E on the other ray so that AD and AE are congruent to each other. If you're doing a construction, don't really put in those hatch marks like what I just did. I'm just doing that so it's easy to tell who's congruent. Okay. And notice this time I actually wrote it a little bit more proper, where I said, hey, do this, and that's the result that you did, unlike in the last example where when we copied the angle, I just said copy the angle instead of giving the result that you get as well. Now, once you go ahead and have 2 line segments on each of the rays, they're the same length only if you're a have a distance function in your model, then you're ready to go ahead and form the line DE. This now guarantees what? It actually guarantees that that triangle AED is an isosceles triangle. So we basically formed an isosceles triangle, but this is sort of a backwards way of doing it, or backwards in the sense of how we constructed the isosceles triangle before. Now, next part of this construction is we actually want a second isosceles triangle. And the second isosceles triangle that we want, we want it to be down here below that line DE. Okay? So at this point, we're actually going to use almost the same thing we did before in our other construction, where we're going to construct that isosceles triangle. There's one difference, though. When we go ahead and construct this isosceles triangle, when we pick this first point, and I'm not going to write the reasons down here until I have the full construction of the isosceles triangle on the bottom, otherwise they're going to keep flying away on you. So here, if we get this point, previously, when we just constructed only the isosceles triangle, we said that point existed by the third congruence axiom, which says you have 3 non-collinear points or 3 points in your geometry that aren't all in the same line. Can we use I3 to get this point in our current situation? What do you guys think? Would I3 currently apply? You're correct. So I3 does not currently apply because we already have 3 points that are not all on the same line, which means I3 has already been used up. You just can't use it again. But do we have something where we could guarantee that this unlabeled point right down there is actually on the opposite side of the line DE as our point A? Any guesses what we could do to guarantee the existence of that point? Right on D. Yep, plane separation. So this line DE would separate your plane into 2 parts. ARD gives you a point on one side, and so you're guaranteed that the other side also has to be non-empty. That means there's at least 1 point. Do we know what that 1 point is? Nope. I'm going to call it P, or point, because I'm super lazy. Okay. So once you have that point, everything else is going to be the same as the construction we just did. So here we'll go ahead and draw in the 2 lines that connect that point back to D and E. We'll then go ahead and copy the smaller of the 2 angles over to the larger of the 2 angles, and then we will get that new point, which we called F right here, and that point F now is going to be the 3rd vertex of an isosceles triangle below the line segment DE. So note here in terms of your steps, here we got that point P exists, and that was plane separation. Everything else is the same as before. So B, we went ahead and formed 2 lines. I'll put them in the same step. So that's DP and PE. And here our construction tool that we used was first instance axiom. Then we said that, hey, angle D, so this would be EDP, is going to be the smaller of the 2 angles. The other angle was DEP, and we knew that was true by proposition 8.5, and that meant we could go ahead and copy our angle EDP to that ray ED, and that was copy an angle, so C4. Now, if you guys are doing construction, notice what I'm about to do for the next step. I went ahead and wrote down all those little pieces and parts because that's what we physically did here, and especially since we changed that first step to plane separation as opposed to the 3rd instance axiom, I needed to go ahead and tell you how I found that first point. But in the actual construction steps, notice I didn't write down any of those subparts. I did it in the picture to show you that I knew what I was doing for the Hilbert construction, but in fact, the very next step that's going to fly in is going to overwrite all of those little subparts. Any guesses what the next and last step of this Hilbert construction would be before I fly it in on this? Yep, we're going to find a last line segment. Specifically, we'll go ahead and find that line segment AF. And that line segment AF, according to our claim, is going to bisect the angle A. Okay? Now, when you do your first several constructions on your own with Hilbert Constructions, please, 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 I would definitely recommend putting in all of those subparts like what we drew in here. But in reality, the picture needs to show all of those steps. But if you condense and just do main steps, that's going to be okay too. All right. So the next thing we're going to do is we're going to look at why this actually works. Before we jump into the why it works, any questions on what we did so far? All right, so let's see why it works. And if you have any questions, I'm going to keep the same picture and the same construction steps here. We're just going to add in the proof part. So putting it into a proof format, the first half of the proof is I'm just going to put in those same construction steps. So here we've got given our angle A. We then picked a point D. We copied that line segment AD to the other side. Went ahead and included that there, cited everything we did. Notice constructed the isosceles triangle down here. I went ahead and just cited that guy. Technically speaking, I really should have said something about the fact that that point is on the opposite side of the line segment is A, but it didn't make it through the editing process of this slide. And then the last thing we did was put in that line segment AF. So here's the things that we know. We know right now that AE and AD are congruent to each other. There's other things, but that's what we know. Next thing is I'm going to claim we know that EF and DF are congruent to each other. Any guesses why that's true? Why would DF and EF be congruent? While you guys are thinking about that, I'll put the other marks in that we had previously. It all comes back to the triangle DEF. What do we know about that triangle DEF, or as I wrote it previously, isosceles? Yes. So what do we know about isosceles triangles? The guys that are opposite their congruent angles are going to be the congruent sides. So that means that was just the definition of isosceles triangles, or an isosceles triangle, since we only had the one that we were looking at. I'm going to claim that the next thing that we have is that line segment AF is congruent to line segment AF. Proper symbols there, a little circle if there's only one line segment involved. So what do you guys think? Does that seem believable? If so, any guesses on why? It's totally something we've done lots and lots in classical geometry. But why would it be true in a Hilbert plane up here in our Hilbert geometry situation? Anybody got a guess? Ooh, it's not the definition of a line. But it's definitely dealing with lines. I would recommend going back and looking at your first 3 congruence axioms, the 3 congruence axioms that deal with line segments. Why would I say that? Because they deal with line segments, and we're dealing with line segments right now. So it would be C2 and 2, remind ourselves, conveniently located right here. For our congruence axiom number 2 says, first part, if line segment AB is congruent to 2 other line segments, then those 2 other line segments are congruent to each other, not applicable. This last part right here is the thing that's applicable for us. This is the thing that says, hey, in terms of symbols, any line segment is congruent to itself. So watch out. If you will need to do anything that feels logic-oriented, it's typically from congruence axiom number 2. Unless it's an inequality, then it's a proposition. So when we come back here, notice what we've got so far. We've got 2 pair of congruent sides, both of which came out of our construction of constructing 2 isosceles triangles, one above and one below line segment DE, and we have a shared side of AF. We've totally set ourselves up to do something. Any guesses on what we've set ourselves up to deal with or use? It should look really familiar, so feel free, if you've got a gut guess from classical geometry, still go for it. We're totally setting ourselves up to deal with congruent triangles, specifically the 2 long and skinny triangles. So these are the ADF and AEF triangles. And if we're trying to get ourselves to say that those 2 triangles are congruent to each other, any guesses what reason we would use? Don't overthink it. Do your best guess. And this is why I keep putting the hatch marks on there. They're trying to be helpful. Yep. So we totally feel like we want to use side, side, side here. And this is why on the previous slide, I made sure to mention, hey, your author gives a proposition 10.1. I don't care if you remember that number or not, but says that in a Hilbert plane, side, side, side does work, which means we can totally use side, side, side right here, which would give you that those two triangles are congruent to each other. Now, if you have that these two triangles are congruent to each other, my really terrible way of marking the two triangles, what does that give you now for free? You already know that all the sides, all the corresponding sides are congruent. What extra does that give you? Hopefully you are all thinking triangles have both sides and angles. Yes. So we are totally going to be using corresponding parts, and from corresponding parts we would get that all three pairs of angles are in fact congruent, or at least the corresponding angles are congruent to each other. Now, we don't care about all the angles. We only care about the angles up here at A. And why is it advantageous for us to get the angles up there at A to both be congruent to each other? So you think back in your head, what were we trying to prove? We're trying to prove that this construction allows us to say that the line segment AF, or the ray AF, or the full line AF, however you want to say it, bisects your angle A. With this piece of information, did we get angle A bisected? Ooh, I got some votes for yes. Any other votes for yes? Hint, there's only two possibilities, yes or no. 3 votes for yes, 4 votes for yes, 5. Okay, a couple of you are voting. Awesome. So yes, if you actually have that both of these two angles are congruent to each other, what does that mean? That means that this particular line segment totally cut your angle A in half, which means typo, which means that your angle A is bisected by your line segment AF. So that was the goal that we were trying to get to, was to show that those two angles at A were congruent to each other, because that would get us one step away from saying, yep, angle A got bisected. No worries. So that would be the idea behind bisecting an angle. Notice, in terms of this, the construction was different from what we would have done in classical geometry because we dealt with constructing an isosceles triangle. The proof was almost the same proof we would have had back in a classical geometry situation, except we didn't cite common notions, we cited Hilbert axioms. So these guys here often will feel very similar to some of the things that we've done back in classical geometry now that we're up in the Hilbert planes. Before we got up to the Hilbert planes, you could still have weirdness occur. That's still a little bit true now, but most of the weird stuff is starting to get pushed off to the side and not allowed. So let's look at one last example before we're done. I think we have time to finish the example of bisecting line. I'm not going to go over the proof. I'm just going to go over the construction on how to do it. So for this one, if you are given some line segment AB, what to do? Well, if you wanted to bisect a line segment back in classical geometry, what did we do? We drew 2 circles. We looked at their intersection points. Pretend those are decent circles. You draw it, and bam, that's where the midpoint of the line is, and that's where it was bisected. Now, what can we not do in Hilbert constructions? We can't use circles. So any guesses what we're going to use instead of circles here? Anybody got a guess? Yep, we are totally going to use isosceles triangles. So if we want to throw an isosceles triangle into the mix here, the only thing we have right now is line segment AB. So we are going to have to construct an isosceles triangle on that base of line segment AB. Now, for this one here, I'm not going to write out all the sub-steps, but we'll do it in the picture. So you pick some point that's not on the line segment AB. If you want to use axiom I3 or the third incidence axiom, you totally can. If you want to use plane separation here, you can do that too. Okay? Then you go ahead and draw in the two resulting line segments that form the triangle. Right now, no guarantees it's an isosceles triangle. You then visibly say it looks like angle A is the smaller of the two angles, so you copy that angle A over here to angle B coming up from your base, which then gives you a new triangle, and by crossbar theorem, you're guaranteed to have that point C right there, in that intersection of the copied ray and the original line segment. This guy is guaranteed to be an isosceles triangle with that construction. And I'm not going to reprove it because we already did that earlier with that first construction example. Now, right now we have one isosceles triangle, and in fact, this part right here, you don't even need anymore because you've got your isosceles triangle. Any guesses what we might do next? Oh, you could. So you could actually at this point go ahead and bisect the angle here at C. So that would be the angle ACB. This would work. When you then wanted to prove your construction would work, it actually would be far more complicated to prove it than with the construction that I'm going to use. Instead, I'm going to do the second suggestion that you guys sent in, which is put a second isosceles triangle on here. So, step 2, we're going to construct a second isosceles triangle, and here's the deal with this one. With a second isosceles triangle, you're going to have to go ahead and pick a point down here that is on the opposite side of the line AB as that point C. So if you were doing the individual breakdown of step 2A, 2B, 2C, etc., here you could not cite the third incidence axiom for this point. You'd have to go ahead and cite plane separation. Now, once you have that unlabeled point, you go ahead and draw in the two line segments that connect that point to the points A and B. No guarantees it's isosceles, so you take your smaller of your two angles at A and at B in this upside down triangle. And it looks visibly like A is the smaller, so we'll go ahead and copy the angle there at A on the bottom to angle B on the bottom. You'll then go ahead and look to see where this ray coming out of B intersects the side you already have. It's guaranteed to have an intersection, and so now we'll get that isosceles triangle D on the bottom. Please note with this construction, there's no guarantee that the isosceles triangle on the top of AB is in any way, shape, or form congruent to the isosceles triangle below the line segment AB. All you've got guaranteed is that you've got two isosceles triangles that share a base, one folded up and one on the bottom. Now, any guesses what the last step of this construction would be? Don't overthink it. The last step, we'll go ahead and draw in that line CD, or technical terms that is form or find the line segment CD. Either one of them is fine. So here we'll go ahead and draw in that line CD. And what we can say here is that line CD bisects AB, or if we're a little bit more precise, we'd say, hey, those two lines actually do have to intersect. And if we were doing the proof of this, which we are not tonight, we would actually have to explain why does this point M exist. And once you have that point M exists, that would be the intersection point of your line A, B, and CD. And it also is going to be the midpoint of line segment AB. Note, there's no guarantees that it's the midpoint of line segment CD, just that it's on both the line segment CD and AB. But that would be the classic way of bisecting a line segment. Yes, you can also bisect the angle up there at C in the first original isosceles triangle, but then when you get into the proof part of it, the proof is a little bit harder than this proof would be. This proof, you would actually just use, actually on this one, you can just look at your different triangles and use something similar to what we did when we proved this construction back in classical geometry, where side, side, side gives you things like, hey, these two triangles are congruent to each other. Then you get that those two angles are congruent to each other. We know those guys are congruent to each other. That one shared, so by side, angle side, you would actually get that M is the midpoint. It would be a little bit longer in the proof, but you could do it that way. But that's all I've got for tonight. There's actually only one example left in section 10, so we'll start off and do that one at the beginning of class on Monday, which is if you're given a line segment, how do you form a line that's perpendicular to that given line segment, and you also have some given point that you have to hit as well. Any questions from you guys? Okay, well, I will hang out for a few minutes if you guys have any questions. If not, though, that is all I've got for us for tonight.